Okay.
I apologize in advance for that.
No, it's great to see you. Yes, yes, yeah.
Otherwise, I could make her talk. So
Okay,
that worked out.
okay, great. Yep.
Then we'll start.
Yep.
Okay. Thank you for this.
Before we leave, we need to take a photo. I took a photo.
Okay,
Yeah.
okay, sure.
Before we leave, after the
Yeah,
session.
yeah, after that.
Yep.
I will stay.
Yeah.
Okay. Okay. Thank you everyone for joining our IISE seminar today. We are really honored to have Professor Young-Jun Son, who is currently the James Solberg Head and also Ransburg Professor from School of Industrial Engineering from Purdue University to visit us and give us this talk. So a little bio about Professor Song. His research mainly focuses on those real-time control of the factory and also enterprise using some digital twins and also multi-paradigm simulations and also modeling of the human machines decisions. And Dr. Song has received numerous rewards. He is a fellow of IISE, and also he received two outstanding young awards. One is from SME, another from IISE. And also he has received several of best papers from different conferences and places. So, and also his research is well funded by different agencies such as NSF, NIST, and U.S. Transportation, right, and Air Force. Yeah. So let's welcome our speaker.
Thank you, Professor Lu, and so thank you for invitation to Wisconsin here. Beautiful campus, beautiful city, right? So, and it's great to see, the older friends. Okay, Professor Siu Zhou, and then I get to meet with and then Laura as well, and then the new faculty and the graduate students. Actually, I get to meet. So again, thank you for invitation. Actually here, so. Multi-paradigm simulation, well, it's a little bit long, but I'm going to talk about some innovations in simulation. Probably you will see some different use of the simulation compared with our IE, the discrete event, the simulations. And so hopefully the students, hope to help form some research interest relevant with this area, or faculty members, always we are looking for the collaboration opportunities, right? So that's actually the goal of the talk. And so simulation, basically we do mostly computer simulation, and second type is the physics, the physical simulation. But the computer simulation, that's a discrete event simulation, our textbook simulation, top down. Entities are usually like the passive, okay? And then agent-based simulation was the same paradigm, but entities that are moving, they are more active. It can also even make actually the decisions. And then continuous simulation, that's a system dynamics, okay, simulation that using differential equations or difference equations, Or nowadays, actually, we use a lot of the physics-based simulation. I don't know any of you play with Unity, Unreal game engine. Okay, that's the type of the simulation. I see a lot of nod from students. Okay, that's the simulation that I'm doing here. And then physical simulation. That's a HIL, hardware in the loop, and a human in the loop. Okay, so Professor Lu mentioned that this real-time controls. I happen to use a simulation where hardware in the loop or human actually can be in the loop as well. And I highlighted some of them in red, and I'm going to touch some of them actually throughout the talk today. Okay, so I'm sure that all of you took the students simulation. That's a MM1, MMC, and then the simplest possible model, and then just entities are just passive, right? Just to go there, wait, and then enter the service when the server is available. If you want to make entity to be a little bit more human-like, okay, if we are wait and patient, impatient, the people may leave, then your simple model like this becomes very, very detailed. That's basically agent. I'm not going to go into much detail of the agent model, but you can use still discrete event simulation to mimic a agent-like behavior. Okay, so that's actually agent versus the discrete event. How about system dynamic and agent-based model? There is a linkage. It's not ad hoc model. This model, I'm using simplest possible system. You can actually, equation-wise, we can derive that although we are using different modeling method, we are doing exactly the same thing. So product diffusion is, okay, this iPhone is not really latest, but whenever iPhone, what is the latest one? I don't know, 14, 15, new one comes out. This really, the goal of the simulation is based on model we want to project, right? This is X time, time. Y axis is the initially nobody, right? Potential adopter. And then initially nobody purchased. Overall, again, people buy. So that's a simple, product diffusion model. So that, new product comes out. People initially nobody, and eventually buy the people. So in the system dynamic model, the way how we represent this adopter behavior is, that's actually this is a variable continuous. Everybody is a full over time. There is this rate, outgoing rate, so that this one increase, therefore this one decrease. Okay, so that's again system dynamic model. Of course, the real system that we want to model is a lot more, the detailed than that, right? What is the corresponding agent-based model? Instead of using this fluid, this is really fluid, right? The continuous variable. We want to discretize that into the customer. It can be 100, it can be 1,000, it can be 10,000. As you increase number of the agents, then actually this is the actual model, and the graph will become smoother, smoother, smoother as you increase the number of the agent, okay? So this simplest possible model, actually we can mathematically derive that although we are using different simulation method, we are actually representing or modeling exactly the same model. So this one, there is a, A, and there is a constant. Outgoing rate is constant. So initially this level is A0, and the R is a constant. So again, it's this R minus D. So that's if you solve the differential equation, this is a system equation, right? So that's actually the equation. So this is again system dynamic model. For the agent model, each agent has this state. So here I'm state A, and you are just leaving this state in different time. And then here, this is the graph for this equation. And if this is 100 agent, they leave the time. So this is the time taken that everybody will leave the system. And that's an equal uniform distribution, right? So throughout the time that entity leave this system equally, so that if you solve, so that's again, it's a uniform distribution here. This is the simplest possible PDF. And if you take the CDF is this time is less than current time, which means accumulation of the agent whose time is shorter means they already left. Okay? So that's a probability multiplied by total number of the agent. That's the people who left the state. So therefore, if you do the mathematical the calculation, then this is your outcome, which is the equation that you based on this differential equation. So system dynamic model, again, this is the simplest possible case, but what you try to mimic using system dynamic model using differential equation is exactly the same as agent-based model for discrete entity using the probability and then expected value. Okay, that's I try to say that we are doing exactly the same thing here. Okay, I gave a very quick overview of the multi-paradigm that I mean. I didn't mention much about the physics-based simulation, but I will show you a little bit later, okay? So second, simulation-based planning and control. So, and then this is actually discrete event simulation, and you will see the hardware in the loop simulation. So I'm going to talk about, that's actually my dissertation long time ago. So I used actually real-time simulation for the controlling automated manufacturing system. At that time, we didn't call DT here I meant digital twin. It seems it's a very, very popular nowadays. So that's actually what we were doing, okay? So using simulation to predict as well as the real-time control, okay? So I'm going to talk about for smart and connected factory first, and then second, I'm going to talk about some of the, UAV, UGV for our, the border control project. Actually, we did with the Air Force. So first system is, this is, typical like CNC machines and conveyor belt and robots, and then I actually put some human here as well because human will continue to be the important components of our system. Okay, so given this smart and connected manufacturing system, I'm gonna talk about how we have been using the digital twin idea for planning as well as the control. This is a very busy slide, so let's look at the left-hand side. Left-hand side is nothing new. This is a traditional way of using simulation, okay? So this is a discrete event simulation representing our system of interest. And then we want to, based on the scenario, we want to do the predictive analysis so that we can solve the production, scheduling problem, reliability, maintenance, scheduling problems, and so on, okay? But again, simulation based on the current status from your database and ERP system, and you can run your simulation to the predictive analysis and do the statistical analysis to identify best policy that you want to implement in your factory. So that's the left-hand side, which is nothing new, right? But the problem that actually we are using is different compared with 20 years ago. Still, small to medium industry, manufacturing company, if you go, right, the part routing, still given a part, the sequence of the resources and machines, it's still mostly fixed. Okay, so that's actually traditional. But smart factory, we have the data, we have powerful computers and edge computings and so on, so that you can actually defer all these decisions as late as possible, just closer to the real time. Okay, so smart factory, the decisions are made online and then based on real-time data. So part sequence is not fixed. Part can either go to machine 1 or machine 2, and we don't make that decision beforehand. We let it be decided in real time. And then from the machine selection, from the part perspective, actually part selection is from the machine perspective. Machine can invite a part. And then from the part perspective, because we have an alternative, we can choose which machine that I want to visit next, okay? So those type, and then many more problems, and I'm going to just leave it here. In terms of the objective function, of course, we look at the productivity, quality, and cost. That's, again, of course, there is a trade-off. But our recent project that we did with one of the local, the defense manufacturing company is minimum energy. So energy, especially place like Arizona, I was at the University of Arizona for 22 years, that energy bill in especially manufacturing companies is a huge. So energy is another part of this objective function that you will see, okay? So talking about energy, this is a real smart meter that we put in the company and we put in our lab, and whatever the algorithm and program that we develop and copy paste and put it to our industry. And then this is a simple CNC machine. Just again, turning, CNC machine. And then if you look at this is 15 hours data, we magnify this one for 3 hours. For one machine, machine is not idle. It is idle during the CNC machining. As you see, the number of the power load actually can be 2 to the 12. It can be huge, right, for the one machine. This company happened to have more than 50 machines. And Arizona, during the summer, they have tons of air conditioning there, so the energy peak one machine, right? And then there is a lot of the idle here, and then that's a high peak actually here, so that this summation of the 50-some machines and air conditioning, and place like Arizona, the energy bill that they pay is not just the integral of energy; it is actually peak. So we need to reduce the peak so that we want to spread out throughout the year, right? But most of industry, if not all, whether they are busy or not busy, they use exactly same NC code, which is designed to maximize their productivity. Even if they are not busy, they want to maximize, right? So that's actually the opportunity here. And then it's a simple production planning problem, but using their energy, can we, spread out, change the schedule without sacrificing our productivity? Of course, we do not want to sacrifice our productivity. But so the kind of the real-time scheduling problem that we look at is, so this is a simple scenario that, part 4 looks like they have an alternative. They can go to the machine B or machine C. Okay, and right now it looks like I cannot go to the machine B and machine C because both of them are occupied. So I need to decide whether I will stay here or go to the buffer so that I will visit this one later. But when we look at actually this one, now I need to decide. I can decide if both of them are available or one of them is available, probably I will just go there. If both of them are available, I need to decide whether I go there where time can be shorter or energy consumption can be smaller. Okay, looking at your the due date as well as the energy consumption, that's actually another dimension that actually we needed to look at it. Those are the kind of the real-time decision that I'm talking about. Okay, so that's actually the planning side, and I want to mention which is different from, addition or consideration of the energy. So now let's look at the right-hand side. The right-hand side is really digital twin. Left-hand side is, again, you run simulation to, conduct the best set of the policies to solve, this real-time, production scheduling problem. Once you found the best policy, then that policy is used by, this is also a simulation. I don't know what Wisconsin you use, Simio, Arena, Automode, I don't know what you use, but we are using this, the commercial simulation, but this simulation is not simulator, it is a controller. It runs in real time. Instead of the simulator, whenever there is an event, it generates a message to the robot, it sends message to the machine conveyor belt, so that this simulator is real-time task generator that drive this real manufacturing system that I talk about. That's actually real digital twin. And I've seen that so many people in many disciplines talk about the digital twin conceptually. If you want to execute digital twin for operation and control, it requires such a detailed synchronization and communication. For example, this is a very simple, one robot and one machine, and you want discrete event simulation in real time to control one robot and one machine. We need these many coordination. Each node is a kind of the state machine. Okay, finite state automata state machine. And then, so this is a simulator which generates the task that I mentioned actually here. And then this is a machine controller. This is a robot actually controller. And then I don't know, anybody heard about the model-driven architecture or like the UML, right? Unified Modeling Language and SysML. That's the idea, okay? That nowadays, when we write the computer code, nobody starts from scratch, right? We start with this model, and then if you click button, then a lot of the major skeleton of the codes are automatically generated. That's a model-driven architecture. So a lot of work that we do is you just specify this coordination from this graph that allow us to generate executable software immediately. Okay, that's actually model-driven, the architecture. So, and then schematic. So I actually simplify the previous graph, and let me show you the cartoon type of the animation here, that how digital twin based on control actually work, okay? So this is, again, Arena Simio auto mode simulation. And then as soon as you run, okay, so this is a software like a state machine that is embedded in the computer, or like this embedded computer, sitting next to the robot, sitting next to the machine. So they need to have this state. And then simulation send a task. Somehow simulation should be able to understand what is going on, right? Because it's a digital twin. Okay, and then it generates a task, ask a robot to, and the robot is really performing the picking operation. It can take 10 seconds, 1 minute. As soon as it is done, the completion message should go back. And then to simplify, I didn't include the OK message back here. But after it is done, OK, then simulation understand, okay, robot completed picking the part, and then it asks machine to open the door. And I don't have so door open, and then after OK is done, simulation understand now robot can put the part, and if it's done, then machine can, okay, robot goes back and machine close door and start the operation, okay? So this type of the very detailed synchronization is needed for us to use the real-time simulation to drive the system. Human in the loop can be same. Human as operator, human can be independent, but in order to coordinate with the supervisor, then human needs to be also part of the this controller as well. Okay, so that was digital twin-based planning and control. Yes, Gabriel. Yeah. Yes, great question. I didn't go into it. We use rules for each of the problem, like I call it machine selection problem or part selection problem. The rule can be first come, first service. Pick the one with the remaining smallest remaining time. Pick the one with the lowest energy amount. So that's actually rules. So for each decision problem, we have multiple rules, right? So the decision is really selecting the best optimum combination of the rule for next planning horizon. And actually, that's a great amount of the research there, because we can do daily basis, but really, okay, it's easy, right? Time-based, every 4 hours, every 8 hours, but there is always the delay in, raw material arrive. There is always, unexpected, the machine breakdown, or so that it really, we need to decide something disturbance happen. Should we replan? Okay, if something happen, if you don't act, that's not good. But if you act too often, that's not good either, right? Because the policy that you have been making is based on the optimum previous policy, right? So that's actually we don't have an explicit schedule, but we have a set of the optimum policy, the rules, okay? So you're welcome. So that was again, manufacturing, but the idea is the same. we use, I'm actually giving this talk from the simulation perspective, right, because multi-paradigm. So previous one was what? Real-time simulation, discrete hardware in the loop. Here is exactly the same. Okay, our NSF program manager moved to the Air Force. It's 17 years ago. At that time, I was looking for application. Now, everybody uses UAV, but 17 years ago, not many people were. So I actually found the UAV. Today, I saw very, very interesting faculty work doing UGVs and so on. So this project is really combination of the, drones together with either autonomous vehicle or man-driven, the border, there is a lot of the people, man driving, but what we can see from the ground, what we can see from the UAV, that's actually the focus here, how we can best, fuse this information from the UAV. But not only, ground vehicle UAV, that was our first project. Our second project is also, there is something called the aerostat. That's even above, and they don't move much, but they can see very broad view. And then also, UAV, once wired, they need to recharge, right? So they need to go back and come back. And so that's actually the 3-layer. And the bottom one is, I focus on, again, this camera vision. But actually, we also put like vibration sensors and thermal imaging sensors so that we can see the animals and people during the night and so on. But again, I will focus on this, the camera, for the bottom and second, and then the third is actually the satellite actually type of the images there. So it's a very, very, very busy, but that's exactly the same as the previous framework that I showed. So bottom one is the hardware that I showed you, and then on the left-hand side is simulation-based planning, and the type of the policy that I mentioned is, of course, different, right? But again, still, left-hand side is planning. Whatever the best set of the policy is used by, this controller to control. In this case, control is next waypoints, series of the waypoints of the UAV, series of the waypoints of the UGV, to, if this is actually one of the goal here is we want to look at like a border area. If there is some drug traffickers or like Yuma, Arizona, there is a lot of the animals, that they can, damage a lot of the, that whatever the things of our interest, we want to use multiple UAV ground vehicle to maximum coverage. We want to, if we can follow all of them, that's the best. But I'm sure that they make a random movement and then so on. So that's actually the goal actually here. So let me show you again the kind of the simulation and the kind of the field testing that we are doing using this simulation. So I don't know anybody does agent-based simulation? So this is a REPEST. Argonne National Lab REPEST. It's, as I said at my first slide, agent-based model is not different from discrete event, but agent is a lot more active, or agent can do even a lot of the detailed decision making. So more active rather than passive. That's So here, there is a little sound there, but you hear the UAVs. But this is actually, if you look, you don't see much. But here, there is a hardware in the loop with a UAV, UGV hardware in the loop, and it has many, many simulated UAVs, many simulated UGV using the kind of the communication. You saw the communication graph for the robot and machine. It's very detailed, right? And then but each individual UAV, UGV, they do not know whether they are communicating with a real UGV or virtual UGV because interface is exactly the same. So the goal here is we want to use this, the same interface to check the scalability. So I can use again. If I want, I can buy 50 UAVs, 50 UGVs, but I don't want, right? Just a couple and then a hardware in the loop, but I want to simulate the rest of the UGV. So that's and the agent. Anybody use Unity and Unreal game engine? Not much. You do. So Okay, this is Unity game engine. So if you go to the Disney World and Disneyland, you see a lot of the virtual reality. That's actually, many of them are programmed by Unity, right, or Unreal. So that's actually exactly the same software that we use. So if I run it, unless you pay attention initially, you cannot tell whether which one is real or which one is a simulation. But this is a game engine. This is already 5 years old, which means today version is way better. And then they add a lot of the modeling capability and interface so that this game engine simulation, its capability gets really good. Okay, so here the top part is a real scene in one of the park in Arizona. And then this is the scene that the UAV actually sees. This is the scene that UGV sees. And then this is a Unity game engine, physics-based simulation model of the park. And we are simulating what UAV is seeing and what UGV is seeing. And I know there are a lot of the machine learning, data analytics experts actually here. So we use the OpenCV, for our crowd detection for the UAV and the individual person detection from the UGV. So if I show so these are the kind of, right, that I said a crowd, crowd can move, crowd can join, crowd can split, crowd can go beyond our detection range, and then everybody can make a random movement, and then we test our, again, detection algorithm for the different kinds of the scenarios, right? So, and then if I show this one, and I skipped a lot of the modeling part, okay, just showing the outcomes and so on. But this is exactly the same scene that you saw. Okay, that actually happened to be student union. UAV really does not fly. We can fly, as you saw in the park, but for this one, and you see the little guy following them, that's actually what little guy's view. So the UGV is actually follow, so that here we try to, again, detect the crowd, and we want to predict crowd movement. This one is an individual, okay, person, and then this information is fused, and then so this is a prediction by the UAV, this is a prediction by UGV, and the red one, it's hard to see, but this is actually coverage probability. If you can follow whether crowd make any random movement, split, join, if that's a 1 means we were able to follow all the time. So red one is always better than the other one, which is we use both UAV as well as UGV information versus you only use a UAV information. In the real world, UAV, what if there is a cloud? What if there is a tree? We lose it, right? Just like a shelter in the park, people enter the shelter. UAV lost actually the view. That's why UGV follow them, and then I can see people may come out right or left, right? So that's actually the idea. So again, in this project, we use both agent-based model as well as we use the game engine, physics-based simulation for the planning and the control. So let's go back to the manufacturing one. We look at only one manufacturing factory. Nowadays, the supply chain is so popular, right? So let's extend this idea. We like a hierarchy, right? Because we want to do the one machine, sell, shop, now supply chain, okay? How can I extend this simulation-based digital twin idea to the supply chain planning and control? So the same thing. Just like we look at robots and machines and conveyor belt, and then we look at each individual component, describing this interaction using UML or finite state machine or state, chart, right? Any time of the coordination, the modeling is actually important. And then for the control, it needs a different type of the model, but let me actually focus on just the simulation model only, right? Because I'm focusing on simulation. So how can I extend this one? So simulation. So this is a simulation of the assembly plant. This is a simulation for the transporter, simulation for the supplier, simulation for the another supplier. And as I said, I don't know what kind of the simulation you use, but we develop web services. We develop services that can be used by, so this is a project with Boeing. Boeing, they run our simulation in Seattle, Boeing commercial, not defense. and then they use our server to link their simulation in Seattle facility, Japan facility, the South Carolina, Charleston, South Carolina facility. And then as you see, for the demo purposes, I put 4 independently running simulation in one computer and I videotape. But in the real world, each of this simulation is independent. But behind the scene, there is a lot of coding is needed. Why? This computer can be a lot faster than the other computer, so that you simulate that this one can be tomorrow and my simulation can be still today, right? And then what if they send the information? It's already outdated. So there is a lot of this time synchronization. Also, good, I think data privacy. This technology is great so that each company, I am collaborator, so I want to collaborate with another company, but still we are a different company. I don't want to share my proprietary data, so that this technology allow that we can exchange information and time so that we can do the supply chain based planning. Okay, but still, we want to hide our important, actually, the data, okay? So that's what's called the distributed simulation. All this one is a textbook simulation, okay? If you are, familiar with simulation, Arena, Simio, okay, AnyLogic, okay, and Game Engine, all of them, okay, we integrate because our services, web services, it can connect to Java-based or other, the languages easily, okay? So that's actually the distributed simulation. And then so another one, this is actually a little bit old work because of some of our, one of my early PhD student work. And then so supply chain, when you do the production planning and distribution planning, right, between supplier, assembly, and then so what we do is you don't want to use integration of the distributed simulation to evaluate your plan in the first stage. If that's a realistic supply chain company, it can be very slow, right? If you want, again, computer gets powerful, you can, if you have a model of each supply chain member, you can run it in a distributed environment to evaluate planning, and then distribution, production planning, you can, use this simulation to evaluate your plans. However, that's a very computationally heavy. So what we did, this actually got a lot of attention, is first you use a system dynamic model. You remember? Okay, system dynamic model is aggregation. Instead of using detail, we use more aggregate model. So, we had actually this planning decisions using only system dynamic model. Still give you good decision, but it's not as detailed accurate. So once we find some good plan, we use more detailed, integrated, distributed simulation to evaluate, these decisions. So that's actually the second way that we have used, okay? So I think I'm trying to use the different multi-paradigm simulation to support this planning and, control the decisions. And one thing I didn't mention much, okay, that I want to still talk about is a human, okay, human-centric system. To me, I think we talk with a few professors actually here, and whether we do the optimization, modeling, and simulation, data analytics, and all the important human the topics, in the future, the system of our interest will be only more human-centric. We still need to do the optimization. We still need to do the modeling and simulation. We still need data analytics, so that systems is really factory. It's a future factory is, right? The human is there, robot, human, cobots, right? So I'm going to talk about the simulation. And again, simulation perspective, right? That not only agent, simple kind of decision. We actually, project that I did with the Air Force with 10 additional faculty, this is a 11 faculty project, is developing human, of course, including psychologists as well. Okay, and then as an engineer, that we actually borrowed all the best. It even includes decision field theory, which is one of the decision theory. Okay, that are used by the mathematical psychologists, and we borrow those different models to best to represent or best to develop our human behavior model. and I happen to use any logic or repass to implement our detailed human decision-making model, okay? So that actually, this is actually framework we kind of completed 2005, long time ago. Since then, we had a lot of the different projects, okay? NSF project to mimic, the Qinghee and Rajan Bhatta for a lot of the hurricane and disaster kind of the, decisions. This is Air Force and NIST about the, man-made, the bomb attack, which shouldn't happen. But again, that's a scenario that was given by, government. And then this is transportation. Okay, when I show this model that a lot of our transportation people, they want to use, our behavior to mimic their both driver behavior as well as a pedestrian behavior. So we have a, couple of the, Federal Highway Administration project as well as one NSF project and so on. So let me show you one simulation of, so this is a simulation perspective. This is a agent-based model, but their model behavior is very, very, very detailed. Okay, that the architecture that I didn't show you, but it has a Bayesian belief network for the situational awareness, running the decision field theory to choose which route, intersection that we will go. Okay, again, I will show you a little bit, but the behind the scene, this is what the simulation looked like, and I missed it, but initially everybody color was blue. So this is a Washington D.C. monument you see here, and you see 8,000 people. That's a July 4th. 8,000 people, they are watching fireworks. And again, that's a scenario, made-up scenario given by the government, okay? And then everybody, their colors were blue, which means normal situation. We are enjoying, okay? And then something happened here. Then people change their color from the blue to pink, means they change their behavior from normal behavior to evacuation behavior. And some people carry question mark. Some people don't carry question mark. Question mark is like me. I'm first time being in this room, so I'm not familiar, so question mark. So if something happened, I will, just follow the everyone go, because I will follow where the crowd go. And if you are familiar, you may decide you will go there, and so on, okay? So that's actually our animation. And then, so behind the scene, so how do we construct always you can ask, how do we know how people, behave? And, again, this kind of the scenario, we don't want to have much data, right? We don't want that instant happen, right? So what do? That's where virtual reality-based experiment comes in. Okay, so what we do, in order to develop this kind of the simulation, what we did was, again, virtual reality, we began, probably 2003, but nowadays everybody do the virtual reality, mixed reality, right, which is great, okay? But, so once you conduct a human experiment, especially like a bombing attack and those scenarios that we don't want to have real data, right? And then once you have it, you calibrate model for the behavior model that I showed you. Okay, that's a human behavior model. And then you combine your environmental data, and then that becomes more realistic, the agent-based model. And that the model is used by NIST at that time, that when something instant happen, what will be the best way to deploy policemen, to minimize the casualty. If there is a second attack, what we should do, and so on. Okay? And then value of information. Okay, that actually, we have actually the value of information that nowadays, I think most of us get this notification, but at that time that what if we share this information, that how much we can, again, to any good, the policy we can actually evaluate. This is our human behavior model that I skipped. Okay, so that it's very actually busy, but nowadays, I know that we have a lot of actual experts here, but what we do actually here is we use a Bayesian belief network. You can use other type of, probably nowadays even, the deep learning kind of the model, but what we do here is this virtual reality environment. Do I have virtual reality environment here? Yes, so virtual reality, this is a virtual reality. you can see that model is a so again, I just want to show you it can be very detailed, and this model is used by this headset. Okay, we use a different headset. Long time ago, this is a Discovery Channel when we had something called the room. You have a room and you wear a goggle, or you don't use goggle. Your room, actually, you can navigate through the situation. So we conduct a lot of still we want to collect the human behavior under different, situation. So we change environmental variable, and we see how people do. We try multiple times, and so basically we try to understand whether this person has more risk-taking behavior or risk-averse behavior, and that becomes our parameter that are used for our behavior model in terms of the situational awareness or perception behavior. I'm sure that my behavior and your behavior will be different, right? So that's actually how we do with this. And then this is a decision field theory model that I mentioned. Actually, here is this is a very simple linear theoretic model by Jerome Bussmeyer. But this model, just like a utility theory, prospective theory, this is very well known in mathematical psychologists. And Bussmeyer, the author, is very happy that we used his model, not just making one-time decision. We use it for the multi-stage planning. What do I mean by multi-stage planning is, so this is the scenario. This is you, and then if you are familiar, when you make a decision, you just don't make one decision. It can be very short, but if I need to evacuate, exit, I can see that, first, should I go there or should I go there? Once I go there, should I go right or left? Once I go there, at least a series of the decision points, right? And then if you are familiar, okay, like you, I'm not familiar. I have no idea whether, that's why my decision will be n equal to 1. I will follow most of you go. But you can quickly to think that, so our model allow you to go through this actually thought process. That's why the author is very, very happy that we use his model. So what we do is, so you are currently here. Let's just suppose you needed to, this is your destination. And then currently what you do is, you look at, should I go to the right, left, here, or front, or back? You just evaluate, you just look around, and then your model, Bayesian belief network that we constructed offline, that represent your perception. So that gives us the parameter that are used for the decision field theory. When the output of the decision field theory is a choice probability of the option. So in this case, it gives you 0.41, 0.09, 0.19, 0.31. So after that, you still need to toss a coin, and then this is a higher probability. It's likely to be chosen. Then, second, you are physically here. You're physically here, but your thoughts are there. If I go there, should I go to the right or left and so on, but with a limited information, okay, because you don't know what the situation there is. So we still use a Bayesian belief network with a limited information to mimic your perception, actually the behavior, okay? So that's actually what I mean by the using decision field theory for the planning actually purposes, okay? So I think last, I already talked about the, now I talk more about the detailed agent-based model to represent highly detailed human behavior model. And I didn't talk much about physics. Actually, you saw bombing, but this one, we cannot go to the desert or park when we do the UAV, UGV. So a lot of times when we develop this algorithm, like a detection and so on, this physics-based simulation is getting better. And I don't show the animation of our, the surgical planning, healthcare work. I didn't include it today, but this gets really good so that, okay, when we do the simulation, there is a lot of the opportunity of using physics-based simulation. So summary, okay, the title was multi-paradigm. What do I mean? Textbook, discrete event simulation, textbook information, but agent-based model, more people doing that, but agent-based model can be simple, or it can be as detailed as the cognitive architecture, okay? The third, I talk about the system dynamic. A lot of the economics kind of the aspect can use, or even production planning, supply chain people, many people use system dynamic, difference equation, differential equations, okay? And then it's not ad hoc model. I just showed that equation-wise, you can, demonstrate that we are modeling exactly the same thing. And second, digital twin. Digital twin, not conceptual, actual implementation is not simple, okay? That because otherwise, robot and machine, we needed to look at every single detail, the coordination. So I showed how simulation can be used for the planning as well as the real-time control purposes. And then I also talk about the supply chain, okay? If each company or facility has its own simulation, if you want, you can just integrate them using web services, okay, to construct the your supply chain simulation, or you can aggregate using system dynamic model. And then last, I use the more detailed, okay, use of the agent-based modeling representing human behavior, and our human behavior. There is still a lot of the opportunity to improve, okay? So I think that's a multi-paradigm simulation that I mentioned, and I talk about the various type of the simulation today, and that concludes my talk. Okay.
Thank you. Any questions?
Yes.
For this multi-paradigm simulation, the simulation model could become pretty complicated. You involve different physics,
yep.
different way to do the simulation.
Yep.
But in general, how can we do tests and validation for such a complex model before we really use it?
That's great. So, so for the system dynamic model, actually the example I just put one of our student dissertation is we really look at the competitive supply chain or collaborative supply chain. So system dynamic model, we used that scenario. So the way how we check the validity of simulation was we used the discrete event simulation. Discrete event simulation can do a lot more detailed modeling. So the same scenario, we model system dynamic and how that works against the output from the discrete event simulation. Of course, discrete event simulation, we also needed to validate with the real situation, real data, right? But that's a discrete event simulation is good system that can be used to validate the system dynamic model. Yes.
Yeah, for the topic you mentioned, aware of energy usage in the plan and control of a manufacturing production system. So how can we save energy? Because in my mind, if you want to produce one product, you always use this much of energy, right?
So actually, this is actually real company. So what they do is, I don't know, you heard about the demand response program. Demand response program that, I don't know, actually, I haven't checked Indiana, but Arizona, you can actually, even individual house, you can sign up demand response. What it does is, right now, if you don't sign up, you just, whatever energy usage month, you take integral. That's how much you pay. Once you do the demand response, your rate is different during the daytime, during the nighttime. So the industry, once they sign up, if they are above, because 2 p.m. August in Arizona, everybody needs energy. So the energy is very, very, very expensive. So energy, so what we do is, let's say you have one product, but you needed to produce 100 of them in the same facility today. If you use the same CNC machine, I mean the NC code, which was developed to always maximize your productivity, then you use it, your energy peak will be like this much, and then your job will end 3 p.m. Versus if you kind of spread, then or you will slow down and you finish at 5 p.m. Of course, you are very busy. We don't want to sacrifice productivity, so that we all still want to use as much energy. But they said, again, our industry partner said, whether they are busy or not, they always use a maximum. So there is a lot of the opportunity to reduce the peak so that their energy cost. Yes.
Okay.
Yep.
Interesting.
That's the concept for smart meter, right?
Smart meter, yes.
Smart meter at the household. like EV charging. I heard because of if all the EV charge at the same time, is price is high, so encourage some EV charge during nights and try to.
That's exactly right. So the one project we did was the people have a flexibility of doing laundry, or don't do the laundry, and because working people, we need to go to work, and we have a limited. But so how do we, different time of energy use? That is something policy of time of use, right? That's exactly right. Yeah.
So I have two questions. One question is you introduced different type of strategy in simulation. In practice, based on use cases, is any guidance like which one, how should we decide which one to use is the most appropriate?
Right. That's a great question. Simulation is all about the data and model validity. If you have a physics-based simulation if you don't have a data, then, right, that all model, you spend all time and model will be kind of useless, right? So if you don't have, so actually the model can be really, it needed to go with the data availability, or you corporate-wise, you determine that, okay, this simulation is really important, then you should require, using IoT that the data will be available. Or data availability is limited here, then you don't have to go deep because so that's another, one way to decide the model. But the simulation, actually, not everybody have developing a valid simulation. That takes a lot of effort. Mm-hmm. Sounds like we are expert, but again, still it takes a lot of effort. So that we need the simulation dedicated the people, okay, and then data should be the available. If they are willing to make that investment, we do know that, right? Simulation can do, and then a computation as well. I mean, this simulation. I have many projects, but our DOT simulation, that simulation has like 2 million driver, right? And the 2 million driver using our behavior that we look at Bayesian belief network, that actually, it takes a long time. So we cannot run that, okay, for the 2 million. So the computation is also an issue. So that, selecting, it really needs to be done by the data availability, expertise, and computational power that they can afford to provide in selecting the simulation, right? And then agent-based model is the most detailed, discrete event simulation. System dynamic, probably initial idea, right? That, causality loop and, right? That initial idea, system dynamic model will be good. Physics-based simulation, again, I mean, I didn't talk about, we use a physics-based simulation for the surgical training. So that model is a very, 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 very detailed, right? And then we use actually that physical model. And then that actually made, hospital, they're willing to, right, invest that much money to mimic real classroom. I mean, the hospital, the surgical room. And then we, again, do all the, haptic, the interface, as well as now this, AI gets better and better so that this patient, we can communicate, right? That for the training tool, not the analysis tool. So many game engine nowadays use to, use as a training tool, but that simulation, we needed to use a game engine. And then when I talk to the high school student nowadays, Unity, those things become more and more popular. Every year that I ask students, that, of course, not everybody, but even high school students, I don't know, they play game and so on, but there are every year more and more kind of students are, exposed to this type of simulation. Okay, so.
So when I was an undergraduate, it's Unity. I use it in my undergraduate thesis. Yeah, I played it. Yeah, in 2009. So yeah, at that time it's quite popular and also very expensive to buy a version. I remembered.
That's right. It's a very also high learning curve. Actually, it takes time to learn, and but it took a while for our students can use it. But all my students spend a lot of time playing with the game engine now, to use develop scenarios. Okay.
So one actually my general concern for the a simulation-based approach, I think if it's a stationary process, I'm pretty sure it can simulate it very well. But if it is non-stationary, like a sudden events, I always concern the simulation model may be too simple, not complicated enough to cover all the scenario. For example, like autonomous driving, right? You can simulate pretty well if there's no like accident events. But if there's sudden some events happening, always you cannot include all kind of like events in your simulation model. Then the simulation, in this case, it cannot be like adaptive enough to those scenarios, like the bomb situation, right? The bomb can, if the situation changes a little bit, the simulation model can be totally wrong.
Right.
So how to address this issue?
No,
yeah.
that's a great point. So that's why actually when, again, we work on the DDDS project together, right? I mean, we use the simulation in offline as much as possible, but online, even our factory simulation. Right now, arena, right, simulation, if you run simulation, always start from, empty. It's always not empty, and then, right, so we need to reach the steady, right, the steady state. But in this simulation, we put a lot of effort. When you click, simulation should start from my current factory in the morning. Oh, machine is busy, not busy, how many Q status, right? So that simulation should really run from the current status, and then you can run. So that's actually, one effort. So answering your question, I think we probably use a lot of the offline kind of the scenario, and then also the using online, and then simulation can do so many different scenario, but we should reduce the scenario as much based on the current real time actually the status, right? So.
Thank you. Let's thanks for Professor Song again for this intriguing talk.
Thank you. Thank you for your invitation again. Thank you.